Hi there, my name is Bart Baesens, and today I'm going to talk about challenges in machine learning for the MIT Quant and AI conference organized by Rebellion Research. And I'm really thankful to my friend Alexander Fleiss for the invitation, for allowing me to give this presentation. First of all, a little bit of information about myself. I'm a professor of big data and analytics at the Catholic University of Leuven in Belgium, which is where I'm situated right now. I'm also a guest lecturer at the University of Southampton in the United Kingdom. I do research on big data and analytics, on credit risk, fraud analytics, and customer lifetime value modeling. And actually, my research focuses both on developing new analytical techniques as well as using those analytical techniques in innovative applications in credit risk, in fraud, in CLV, etc. If you want to know more about my research, you can have a look at my website, dataminingapps.com, where you're going to find the various themes we do research on, as well as links to some of my presentations, slides, books, etc. And in fact, here you can see some of the books that I have published. My most recent book is on managing model risk, which I will briefly touch upon during this presentation. But I also have a few books on credit risk, on web scraping, fraud analytics, analytics in a big data world, profit-driven analytics, and principles of database management. You can find all these books on Amazon in case you are interested. I also have my own online course platform. It's called bluecourses.com, where we have various types of courses related to machine learning, fraud analytics, recommender systems, customer lifetime value modeling, text analytics, and credit risk. These courses essentially consist of pre-recorded videos, which you can watch as many times you like during 1 year. So you get unlimited access during 1 year. You also get a certificate that is then being posted to your LinkedIn account. And part of our revenue, we invest in sustainability. More specifically, we invest 20% of our EBIT, of our earnings before interest and taxes, to companies cleaning up the oceans from plastic, such as WWF, Waste-Free Oceans, etc. So feel free to have a look at this website in case you want to know more about these courses. Today I'm going to talk about challenges in machine learning, and we're going to start by briefly refreshing the machine learning process model. Then we're going to talk about machine learning model requirements, model risk, and we're going to finish with some closing thoughts. The machine learning process model is basically highlighted right here. And the first thing that you should do is you should clearly identify your business problem. What is the problem that you want to tackle with machine learning, with analytics or data science? The terms are typically used interchangeably. Maybe you want to detect fraud. If you want to detect fraud, you have to carefully specify what kind of fraud you want to detect. Do you want to detect payment transactions fraud? Do you want to detect tax avoidance? Do you want to detect credit card fraud, etc.? Next, you have to identify the various data sources. Are you going to use transactional data, behavioral data, maybe some metadata? Metadata is something that is typically very important in a fraud detection setting. Maybe some geographical data, maybe some imagery, unstructured data, maybe some external data, data that you can obtain from Google, for example. So identifying data is really a very important step in this process model, as it is this very data that will be used to build your machine learning model. So all of this data is then brought together into a staging area. The staging area can be a data warehouse, can be an Excel file, can be a text file, a CSV file, but it just gives you a comprehensive view on all data available. Next, you will have to clean the data. Cleaning the data means that you're going to get rid of any types of inconsistencies, like duplicate data, like missing values, like outliers, etc. The next step is that you're going to enrich or transform the data. That means that you're going to aggregate geographical data, for example, or that you're going to do some feature engineering. You're going to, based upon the birth date, you're going to calculate the age feature. Or maybe in marketing or fraud detection, you're going to calculate the RFM features, recency of a transaction, frequency of a transaction, and monetary value of a transaction. Three types of features that are commonly used in market segmentation, marketing analytics, but also fraud analytics. because they are typically very much related to a target variable, like churn, like response, or fraud. And then you're going to analyze the data. You're going to analyze the data using a machine learning technique that tries to differentiate the red dots from the green dots. Think about a logistic regression model. Think about a decision tree, an extreme gradient boosting model, which is very popular nowadays, or maybe even a neural network or a deep learning neural network. Deep learning neural networks, which have especially proven their worth when analyzing unstructured data such as imagery, multimedia files, etc. And once you've come up with this machine learning model, you will then interpret it together with the business expert. You will evaluate it, you will calculate its performance, and then you will put it into production. You will put it into production, you will monitor it, etc. All of this is part of the post-processing step. So we basically have three steps: pre-processing, machine learning, and post-processing. Usually, most of the time that you spend doing analytical modeling is done doing pre-processing. And this is very important because all the decisions you make then will have an impact on the performance of the model that you will develop. So what are now the model requirements? Well, the first important model requirement is statistical performance. An analytical model should measure patterns as they are in the data in a statistically reliable way. That means that here we're going to look at things like likelihood ratio statistics, at p-values, maybe at lift curves, maybe at receiver operating characteristic curves, etc. So there's a whole plethora of statistical evaluation criteria that are available for classification models, for regression models, for clustering models, etc. But if you want to successfully deploy machine learning models in industry, you also need to look at their interpretability, especially when you're doing fraud detection. Because once you detected the fraud, you want to prevent fraud. So you want to understand what are the patterns that lie underneath the very complex machine learning models to make sure that you can start your fight against fraud. And sometimes either you use a very simple machine learning model that is very interpretable, but maybe a little bit less powerful, or you use a more powerful machine learning model that is more complex and which you have to complement with all kinds of explanatory facilities. Next, we have operational efficiency. Operational efficiency relates to how quickly we can run the machine learning model, how much time is needed to run the model. Can we use the model for online real-time scoring? That's part of operational efficiency. Profitability relates to the bottom line impact. How much money is my analytical model giving me? How much profit is it giving me? Or how much does it allow me to cut costs? And finally, also very important, privacy and ethical concerns, because there's more and more data available, open and external data, for example, there's more and more privacy and ethical challenges that we have to deal with. So in terms of statistical performance, as I said, we can look at all kinds of statistical performance metrics. And if you would challenge me, I can enumerate quite a lot. But here in a regression context, we would be thinking about R-squared values, about mean squared errors, about mean absolute deviation, about Pearson correlation, etc. In a classification setting, think about churn prediction. We're thinking about lift curves, top decile lift, receiver operating characteristic curves, sensitivity, specificity, precision, recall, and so on. And basically, all these measures tell us something about the statistical value, the statistical worth of the machine learning model that we are working with. But, as I already briefly mentioned, there's more to having a successful analytical or machine learning model. We should also look at model interpretation. And to be a little bit more precise, whether you need model interpretation or not also depends upon the application. Certain types of applications do not require model interpretation, like response modeling or recommender systems. The goal of response modeling is to see whether somebody is likely to respond to a marketing campaign, yes or no, whether he or she is likely to open an email, likely to read an email, likely to click on a link in the email, likely to download a PDF from your website, or maybe the ultimate response, buy the product that you offer on your website, the product or service. For response modeling, I also recommend the systems, which are the systems adopted by Netflix or Amazon, for example. You can perfectly do with black box models. You just want to make sure that you have a model that predicts who is going to respond or what movie or book to recommend. But in very mission critical strategic applications like credit risk, medical diagnosis, or fraud detection, we need white box models. White box models that are going to clearly tell us why a certain customer is considered to be a defaulter or a good payer, why a certain medical diagnosis is diagnosis A, think about cancer or not cancer, why a certain transaction is considered to be fraudulent versus non-fraudulent. So for these, we need white box models. And when I say white box models, I'm referring to models such as logistic regression and decision trees. Those are simple models, often not, not the most state of the art in terms of performance, but not bad either. But their key characteristic is that they're transparent, is that they're easy readable. If you really want to go for model performance, then you should resort to very complex models like extreme gradient boosting, random forest, or neural networks and their deep learning variants. These are typically examples of high-performing models, so they will allow to detect very complex patterns in the data, but it comes at a cost because they're black box models. So if you want to open up these black box models, there's again a plethora of techniques like partial dependence plots, which are going to show you how sensitive the model outputs are with respect to some of the variables. ICE plots, which are a variant thereof, individual conditional expectation plots, Shapley values, which are nowadays very popular in industry, and which are going to show you the contribution of a variable conditional on the presence of other variables, and line. So these are all explanatory facilities that allow you to complement complex black box models with some readability. But obviously, they are also not perfect because many of these interpretability mechanisms suffer from what we call multicollinearity problems. Multicollinearity is a problem where the effect of a variable is spread out across multiple correlated variables. So also, these explanatory facilities will have trouble to properly highlight how a variable actually now contributes to the prediction because the effect of a variable may be spread out or distributed across multiple correlated variables exactly because of the multicollinearity. In my PhD thesis, which already dates back to 2003, I worked on this very aspect of interpretability. And what I studied was how we can start from a complex model, like a neural network, or nowadays a deep learning neural network, and add some interpretability to there. And the representation mechanism that I chose in my PhD thesis was if-then rules. If-then rules, as you can get them out from a decision tree, are very interpretable because they precisely tell you why a customer is classified as a churner, as a non-churner, as a fraudster, as a non-fraudster, etc. So we started off with a very powerful neural network, and we all know that neural networks are universal approximators because they can approximate any function to any desired degree of accuracy over a compact interval. And then we learned a high-performing neural network and then try to extract if-then rules from that. So that way we try to combine the best of both worlds. We try to combine the performance of the neural network with the readability of the if-then rules. And if you want to have more information, I'm happy to refer you to my website, dataminingapps.com, where you can download a copy of my PhD for free. And here you can see the goal. In my PhD, we used neural networks for credit scoring. That's very ambitious because in credit scoring, we need white box models, right? Regulators, national and international regulators will require us to use white box models, which perfectly explain why a customer is either denied credit or accepted for credit. But we started from a neural network because we first wanted to focus on performance. And the way we quantified performance was by means of the area under the ROC curve. And then once we have trained the network, and here you can see the network with the various inputs, with a hidden layer, and with an output layer, which gives us both classifications. Once we had this complex model, we used various types of rule extraction techniques rule extraction techniques that allowed us to model how the neural network thinks. Because by looking at those numbers and by looking at all the complex transformations that take place in each of the nodes, is not going to give us any interpretability. So then, by extracting rules from that neural network, here we can have a lot more readable information of when an applicant is considered to be a bad or a good payer. So here you can see rules that clearly specify why an applicant is labeled as a bad payer. Those were rules that were extracted from the neural network that we saw right here on my previous slide. So it is those rules that tell us exactly how the neural network thinks. And in my PhD, we also made sure that the neural networks did not lose any predictive power when compared to the neural network. In other words, this rule set gave us almost exactly the same performance as the neural network they were extracted from. So that's a lot more readable than the network itself. But in my PhD, we wanted to take it even one step further. We wanted to also represent the rules in a more intuitive, user-friendly format. And what we did was we used decision tables, as you can see right here. This is a decision table, which is exactly representing the same knowledge as the rules we have right here, but now in a tabular format. And that's very handy, very user-friendly, and very transparent, because it tells us if a person has a certain amount on the savings account, which is bigger than 12.40 euro, he or she is labeled as a good payer. If it's less than or equal to 12.40 euro, we have to look at the economic sector that the person is working in. Is it a sector C, which was considered to be a very risky sector, or an other sector? If it's sector C, the applicant is bad. If it's another sector, we have to look at the purpose. If the purpose is cash provisioning, then we have to look at the term. If the purpose is second-hand car, the term doesn't matter, but we have to look at the number of years client. This is an example of a decision table that you navigate in a top-down way to come up with a classification whether the applicant is actually a good or a bad payer. And it's a perfect representation of the knowledge that was captured in the neural network. In other words, now we have a white box transparent model that perfectly tells us how the neural network thinks. Again, the techniques that we used already in 2003, I think are still very useful today, even when we work with models like XGBoost or deep learning neural networks. Operational efficiency relates to the speed of model execution. I'm going to tell you a story about social network analytics. In my research team, we do a lot of research on social network analytics. And when we say social networks, we're not referring to social media like Facebook, Twitter, Instagram, whatever, but we're looking at networks between entities. And we once built a social network analytics model in credit card fraud detection. So we looked at credit cards were one node, um, we looked at merchants that were another node, and we looked at a transaction that then represented a link between a credit card and a merchant. And we developed a very sophisticated social network model that allowed us to see how fraud propagated through that network of transactions. It was a very powerful machine learning model with AUC values above 85%, but it lacked operational efficiency because when a credit card was scanned to make a transaction, the whole network had to be constructed, all the statistical or machine learning activities had to be undertaken, and that required quite a bit of time. And there we were faced with an operational efficiency constraint that stated that we should be able to make a fraud classification within 8 seconds. Because of the complexity of the social network model, we were not capable to do that. So we had to sacrifice part of our predictive performance, part of the statistical performance in return for operational efficiency. So operational efficiency can also be a very important criterion to help you decide upon the quality of the machine learning model. In certain types of settings, you should be able to quickly make decisions like when you're going to block a credit card transaction, or in an online credit setting, for example, if you want when you want to approve an online loan application, you want to make that decision as quickly as possible. Again, much like when we discussed interpretability, it does depend upon the setting, so it's less crucial in settings such as churn prediction or response modeling, where we typically have some time available to make a prediction as to whether somebody's going to churn yes or not, or whether somebody's going to respond to a marketing campaign yes or not. And then we have profitability. Again, as I mentioned earlier, many machine learning models are evaluated in terms of R squared, ROC curves, and lift curves. And though these tell us something about the statistical performance of the models, they don't tell us anything about the profitability. And in fact, at the end of the day, you want machine learning models that contribute to profitability. So, in other words, we want to look at the costs and the benefits related to the classification, to classifying a customer as a tuner or non-tuner. You can classify a customer as a tuner or non-tuner, and this customer can then turn out to be either a tuner or a non-tuner. So you have this confusion matrix with 4 different types of cells: predicted tuner, yes or no; actual tuner, yes or no; where we have the true positives, true negative, false positives, and false positives, false positives and false negatives. And each of them can come with certain types of costs and benefits. So in order to properly take into account profitability, we need to look at the costs or the profit for each of those decisions. And the idea is then to create a performance metric that takes into account profit. And we can use that profit measure then in 2 possible ways. We can use the profit measure to select the best model. We just set aside a validation set, we build our machine learning model, and then we select the most profitable model on the validation set using the profit metric that we developed. A little bit more ambitious and interesting is to directly embed the profit measure in the machine learning model itself, and to make sure that the statistical or machine learning model directly optimizes profit instead of a rather meaningless statistical objective function. And in our past research, we have developed profit measures for 3 different types of applications. We have developed profit measures together with my colleague, ex-PhDs Thomas Verbraken and Wouter Verbeke, for churn prediction. And then we extended this profit measure for credit scoring. And recently, we have also developed profit measures for fraud detection. So if you're interested in any of these profit measures, feel free to drop me an email and I can send you a link to any of the publications on the topic. And besides developing those profit measures for churn, credit risk, and fraud, we even took it one step further because we integrated profit directly into the model construction itself. And to that end, we used 2 very interpretable models because we consider interpretability still as a very important criterion in machine learning, as I already mentioned. So what I did, or what we did, was we built logistic regression and 3 classifiers that directly included the expected maximum profit, or EMPC, per customer in the model construction step. And that way, we developed ProfLogit and Prof3. Prof3 is an extension of decision trees, which is optimizing profit rather than optimizing impurity or minimizing impurity based upon gain, entropy, Gini, chi-square statistics, and so on. Likewise, we have developed ProfLogit, which is directly optimizing profit rather than some rather meaningless maximum likelihood function. You can find the links to both publications right here. And if you're interested, I also wish to add that both Prof3 and ProfLogit are available in open source format on GitHub. So if you just Google them, you will find R and Python applications or R and Python scripts of both algorithms. And when we build models using, for example, Prof3, you will see that the models are different than the models that we built with classical decision tree algorithms, because those are algorithms because Prof3 directly optimizes profit. Here, for example, you can see a classification and regression tree, which is built by maximizing the purity as it relies on the Gini coefficient in CART. And you can see this is a classical classification and regression tree to predict whether a customer is going to be a churner, yes or no. And the expected maximum profit per customer, as it comes with the tree, is about 12.58 euros. This is a classical regression tree. Then we contrast this with a prof tree, with a tree that comes out of our Prof tree algorithm. And you can see that using the same data set, this Prof tree is actually giving us a 1.90 euro difference in profit, higher profit in other words. So imagine that you have hundreds of thousands of customers. Obviously, this will result into a substantial profit gain. And what's also very important is that the splits are different. So Prof tree, because it inherently optimizes another criterion, in this case profit rather than impurity, you will also see that the splits become profit driven. So here you can see a split which is going to consider the average revenue, then the region and the amount overdue, which is totally different than what we have right there. So that's a clear illustration of how profit driven machine learning can help you make other decisions as traditional machine learning models. Since more and more data becomes available, there we have more and more privacy and ethical challenges that pop up. In Europe, we have the global data protection and regulation guidelines that tell us when what data can be used for what purpose. But it can become quite challenging. Think about example questions like, can we use gender or age in insurance and credit scoring? Both are typically highly predictive, male or more risky than non-male. Age is very predictive in credit scoring. The older you get, the more credit worthy you get, usually. Most Western countries will not allow you to use age in any credit scoring model. But what certain banks then do is they use variables like number of years client. Obviously, a predictor or a variable number of years client is highly correlated to age. So can we use number of years client as some kind of factor that is implicitly capturing an age effect? These are questions that many regulators face nowadays. A friend of mine, a colleague professor, showed that what you like on Facebook can have impact on your default risk and credit scoring. But can we use Facebook or Twitter data for insurance or credit scoring purposes? It's not very clear. Can we use Google Street View data in insurance or credit scoring? There's been some research, for example, that allows you to profile the economic wealth of certain neighborhoods by looking at cars as they pop up in Google Street View images. Can we use that to profile economic wealth of neighborhoods and then use that to, for example, model the loss given default, LGD, which is one of the key parameters in credit risk? Can we look at Google Street View data and look at, for example, the facade of your house or your real estate property to help define the loan to value ratio, which is again a key predictor to predict LGD? In a recent study with a PhD student, we studied whether we can use phone detail records, CDR data we call it, call detail records, for credit scoring purposes. Using the consent of customers from a South American telco provider, we were allowed to see whether who you call impacts your credit risk. And in fact, we found that who you call has an impact on your default risk, on whether you're going to default on your credit obligation, yes or no. And though this may sound very privacy intrusive at first sight, closer inspection reveals that it could also bring an opportunity. Because think about developing countries where banks do not have historical data available about their customers. If a bank does not have any data available, it cannot give you credit. But if it could get access to your phone call detail records, maybe the bank will be willing to give you access to credit. So phone call detail records can actually also be a means towards financial inclusion to minorities, to people joining the credit market for the first time, or even to people in developing countries where banks have no historical data available whatsoever. So what may seem like a privacy or ethical challenge could also be an opportunity instead. Feature engineering is something that me and my colleagues do a lot of work on recently. And the goal of feature engineering is to transform your dataset variables into features that are very much correlated to the target that you wish to study. Feature engineering is something that you may do for two different types of purposes: to improve the statistical accuracy or even the profitability of your model, but also to contribute to better interpretability. A feature is a derived data element. Like based upon the date of birth, you can derive the age. Transactional data can allow us to calculate the RFM features. Recency, how long ago since a transaction was made. Frequency, how frequently are transactions made. And monetary, what's the intensity or the monetary value of a transaction. The RFM features have been very popular in marketing analytics for customer segmentation, for churn prediction and response modeling, but also in fraud analytics. And those features typically will allow you to boost the performance of your machine learning models, as I said, either in terms of accuracy or interpretability. It's my finding, or it's my strong conviction that the best way to improve the performance of any analytical or machine learning model is by designing smart features. And we can do that manually, whereby the data scientist will closely collaborate with the business expert, or we can do that fully automated. There exist automated ways of doing feature engineering. And essentially, what deep learning neural networks do is actually learn very complex, unfortunately, black box features in your data. And here you can see an example that I borrowed from KD Nuggets, whereby X and Y represent geographical coordinates. And at the center of the plot, there's a supermarket. A supermarket located where X and Y equal 0. The blue dots represent the profitable customers, whereas the orange dots represent the non-profitable customers. And obviously, it's quite obvious that profitable customers live in close proximity to the supermarket, whereas non-profitable customers live further away from the supermarket. And what's distinguishing both is basically a circle, as you can see that there. Now, if you would offer this data set to a logistic regression or a decision tree algorithm, it would have a lot of problems to differentiate between the blue, the profitable customers, and the non-blue, the orange, or the non-profitable customers, because logistic regression assumes a linear decision boundary, whereas a decision tree assumes a decision boundary or a set of decision boundaries which are orthogonal to the axes. So either we have to resort to very complex techniques like deep learning models, or we can think of a smart way to create very powerful features that will allow us to make a linear separation between profitable and non-profitable customers. And one way to create smart features would be to represent the whole data set in polar coordinates. Polar coordinates r and theta. R represents the size of the vector, theta represents the angle of the vector versus the origin. And then you can see that we have a linear separation where everything to the left is considered as blue or profitable, and everything to the right is considered to be orange or non-profitable. Here you can see our data set being represented in polar coordinates. So we created two features, the polar coordinates, that allow us to separate our data in a linear way. That's one example of very easy, straightforward feature engineering, which contributes to the accuracy of our model. Model risk is also a very important topic, and it's a topic we do quite a lot of research on. And it was triggered by a FICO report in 2021, which stated that 65% of the companies cannot explain how specific artificial intelligence model decisions or predictions are made. 73% struggle to get executive support for prioritizing AI ethics, something that is very important, as I already discussed. Only 20% monitor or backtest analytical models that are in production, and 30% of the organizations report an increase in model security issues, or in other words, in adversarial and other attacks against their models. So these numbers are kind of worrying, and in a certain way, they all relate to model risk. So that's why we published a book on that and managing model risk, which is available on Amazon. And in the book, we define model risk as the risk of expected or unexpected loss resulting from the inadequate development or usage of machine learning models across all business units and activities of a company. And model risk as such can then be decomposed across the entire model development life cycle. First of all, there's data risk. Every data set that we use in machine learning is biased. And I like to read a lot about World War One, World War Two, and just to show you an example. Here you can see an example of a plane that was sent out across Germany to do a bombing raid. And as it returned back home to its Royal Air Force Base in England, you can see all the red dots which indicate where the plane got hit by enemy fighter. And as the plane returned, obviously, Royal Air Force engineers were wondering where they should put extra armor to the plane, where they should reinforce the plane to make sure that more planes survive or successfully return back home from bombing raids on Germany. And where should they reinforce the plane? Should they reinforce the plane where it got hit and successfully returned? In other words, at the red dots? No, because the planes that return are actually a biased sample. Those are the ones that made it. The ones that didn't make it most likely suffered damage on all the white regions because those are the ones, like think about the engines, when the engines were hit, for example, those are the ones that went down. So if Royal Air Force engineers have to decide where they have to put extra armor, it's not on the red damaged spots because those are the ones that made it back home, but it's on the undamaged spots because those are the ones that didn't make it back home. So it perfectly illustrates my point of data bias. And sometimes data is biased without you as an expert or as a data scientist being aware of it. And data bias is something that sometimes we can cope with it up to a certain extent, but most of the times we cannot perfectly get rid of it. Every sample is biased because it's conditional on the strategy the firm was adopting at that very moment, on the endogenous characteristics of the population, but also on the external environment during which the sample was taken. Think about the macroeconomic environment, for example, something that is very relevant nowadays. So data bias and dealing with it is a very important component of data risk. Another important component is lack of predictive power. At the end of the day, what we want to do is we want to predict human behavior. And human behavior can sometimes be very hard to predict because we have limited data available, because of the fact that human behavior can be irrational. So if you're facing lack of predictive power, you can try and gather more data, external data, unstructured data, multimedia data. You can try to do some very clever feature engineering, which we also describe in our book, like Yeo-Johnson transformations. Think about very clever data transformations that will enrich the power of your data. Or we can try to combine the data we have with domain expertise, with business expertise, with the expertise that business experts like fraud investigators, like marketeers, like credit decision makers have gathered throughout the past few years. And a technique which lends itself very well to do this is Bayesian networks. Bayesian networks are white box probabilistic models that allow you to basically combine knowledge from domain experts with knowledge from data. Development risk relates to the software that you're going to use and the implementations in software. Um, it relates to open source versus commercial software. Open source software is software that is available for free, which is good, but it comes with certain issues as well because you don't necessarily have any quality guarantees. Commercial software comes with a price, but obviously it has been thoroughly tested, validated, it's in compliance with regulatory guidelines, which is again to its benefit. Development risk also relates to programming errors and also to not being too much blinded by new developments. It's not because it's a new fancy development that you should immediately jump on that bandwagon. Think about NoSQL databases that were originally very popular in all kinds of commercial literature, but I mean, not many successful implementations thereof have been seen in industry yet. And the same essentially applies to deep learning. Security risk relates to model outsmarting. It relates to fraudsters that try to understand how your model labels transactions as fraudulent or not, and then tries to outsmart them. It relates to model exfiltration. Many models are being exposed by means of APIs on the internet. And there's been some literature that has shown that if you expose a model through an API, by repetitively calling the API, you can actually learn what the model is. This is what we call model exfiltration, or stealing a model by means of its API, or model theft. Just as we have denial of service attacks to make sure that a website goes down because of too much traffic, we can also create denial of prediction attacks to make sure that a predictive model, a machine learning model, is going to crash by providing it bad input, by overloading it with prediction requests, and so on. That's an example of a denial of prediction attack, which we also discuss in our book. Finally, there's also managerial risk, which relates to regulation risk. Think about privacy and ethics, but think about also all kinds of regulation that is continuously changing, right? Regulation about machine learning models is currently being developed by various types of governmental and intergovernmental institutions. So we have to be on the continuous lookout for new developments in the area. It also relates to model ethics, like to what extent can what data be used for what predictive purpose. And also, more and more, we have to look at sustainability, or for example, the impact of climate change and ecological risk, especially in credit risk, weather forecasting, but also when we are estimating deep learning models, as many deep learning models require tons of parameters to be estimated, which brings about a pretty large carbon footprint. Nowadays, there exist packages in Python. I think Carbon Tracker is one of them that allow you to track the carbon footprint of some of your Python routines that you're calling. So this is actually bringing us to the conclusions of this rather small contribution, in which we spoke about the machine learning process model, data pre-processing, model construction or machine learning, and post-processing. We zoomed into the model requirements. We introduced model risk as a very important component, which is kind of spread out throughout the entire machine learning process model. And we finished with some closing thoughts. In case you want to have more information about any of the topics that I've discussed during this talk, I'm happy to refer you to my Blue Courses website, where you find various online courses which you can start right away. You can just sign on, start right away. All of them consist of 4 to 6 hours of pre-recorded videos with R, Python, and SAS scripts, and you have access upon registration to each of these courses during 1 year. If you're interested in the slides of this presentation, you can also send me an email, or in case you have other questions, don't hesitate to send me an email. Thank you very much.